All right, we'll get started with the next talk. I'm pleased to introduce Igor Oliveira, who's going to be giving us a talk about Idris. And as cloud computing becomes ever pervasive, big topic is how to keep your computations on cloud data secure. So looking forward to this talk.
Hi all. Like, I'm happy here to be talking. It's a great conference. I hope you all are starving for knowledge. So it talks about two things I am passionate about: Idris and hardware security. To be honest, few people would put hardware and security in the same sentence because you know. I promise not to rant too much about it, but yeah. So I'm going to talk about how we can put a piece of Idris code inside SGX, Intel Enclave. I'm going to talk a little bit more about what it is and so on and so forth. But before that, a bit about myself. I am the technology partner of a company called Working Co. We're based here in New York, and we basically work with products, any kind of products. And one thing we also think about is the user and the user privacy and the user security, and we explore a bunch of stuff. And this talk is one of our exploration the security land. A little bit about the outline. So we're going to cover a few things. The first thing is the why. Why? Okay. But now I not see my slides anymore. Let's wait a second. That's right. Yeah, so we're going to cover a few things in this talk. The first one is why this talk is relevant, especially thinking about the cloud and its threat model. The how, a little bit about what is SGX and what it is SGX and what is enclaves. So for this talk, I'm going to talk about SGX and enclaves as the same thing. So sometimes I'm going to talk SGX, other times I'm going to talk about use the word enclaves. A little bit about Idris and the challenge about running Idris inside the SGX Enclave, and why Idris is a smart choice about running enclaves. So the cloud. So this is the cloud, the promised land, right? Everything runs in the cloud these days. And personally, I think it's great. From fintechs website, anyone can easily instantiate a machine and deploy the code to it. And when the virtualization came and also containerization came, it became the de facto standard. So the whole process of deploying and running codes in the cloud became even more easier. And now we even have Lambdas, Azure, all this kind of stuff. That being said, the cloud is not bug-free. We have a bunch of issues in the cloud and AWS and things like that. So what that means, the cloud is just Mars computer. So for us, the cloud is an untrusted party. If you think using cryptographic words, so we should not trust the cloud, especially thinking if we are working with cryptographic schemes and things like that. We don't have any guarantees that the code that runs there in the cloud has any integrity or even confidentiality guarantees. A container, virtual machine could be hacked and its code could be modified. Even the cloud provider could be hacked, or someone could ask the cloud provider to modify the client's code. And I say, sorry. By the way, when I say the code can be modified, I already see in the face of the cryptocurrency folks here, rolling their eyes, shaking their heads. It's a different threat model. I am talking about running a piece of code in someone's CPU, in the cloud. It's not about ledge. It's not about distributed code. It's not about peer-to-peer. It's running a piece of code inside somewhere machine. But before I start to talk about the enclaves and SGX, we need to understand how software privileges work, especially in the cloud. The interesting thing about how it works is because each privilege level, is strictly more powerful than ones below it. So, for example, uh, if you are in the ring tree, the OS kernel in the ring one can read and modify everything from the ring tree. Or the hypervisor can modify the kernel, they can modify the application. The SGX Enclave here, it lives in the ring tree, however, it's self-contained. So even besides its living ring tree, the other rings are not able to modify it. So what I'm trying to say here is, if ring zero, the kernel is compromised, we are screwed. There's nothing you can do unless you are inside the SGX Enclave. And the SGX Enclave, basically SGX Enclaves, it's all about trusted computing. They are basically secure remote computation. And secure remote computation is the problem of executing software on remote computer, owned and maintained by interested parties. So if I want to run a software in the cloud or somewhere on a machine, or even the machine close to me, but it's untrusted, it's the concept of secure remote computation. However, we need to have few integrity and confidentiality guarantees. So when we think about secure remote computation, we need, again, integrity and confidentiality guarantees. In general setting, secure remote computation isn't solving the problem. There are few solutions, but they are not performatic. For example, there is one thing called homomorphic encryption. So you can make few operations using homomorphic encryption. For example, I can multiply two numbers without decrypting the data. However, it consumes sometimes 20 gigabytes of memory and a lot of CPU. So it's not feasible right now. And also interesting thing about trust computing is because it's not nil. So this is the Orange Book. It's from the 80s. So US researchers and the DoD are thinking about it since late 80s. And in the late 90s, a bunch of hardware vendors created one thing called a Trust Computing Platform Alliance to specify how trust computing should work inside CPUs. So AMD, Intel, I think that time Compact as well. So it's not something new. People are investigate about how they can make it feasible and usable in the day-to-day work. But how it works, the whole idea of secure computation is not that hard. So basically there are three main parties: the data owner, the software provider, and the infrastructure owner. So the data owner and software provider can be the same person, the same entity. The infrastructure owner could be the cloud, for example. So the whole idea here is, I want to send a computation to the cloud, and I want to receive it back and be able to validate if that code computation was modified or not, if the data was modified or not. I want to have few guarantees about it, about, again, confidentiality and integrity. So if I send to the cloud, please add 1 + 1. When I receive the data back, I'll be able to know if instead of 1 by 1, 1 + 1, the cloud, the infrastructure owner, changed my code and it became 1 + 3, 1 + 4. So this is the problem of secure remote computation. How can we send a code to the cloud and data to the cloud and return back the data without the owner, the infrastructure owner, the cloud, not be able to modify my code? And these are a few interesting properties about trust computing. So the first one is the endorsement key. Basically is when the manufacturer, the CPU manufacturer, creates a chip, it inserts inside it a public and private key pair, and it can never change. So it's there inside the chip, and it's used for attestation. So it's used to verify if the code there was not modified. Secure I/O, basically all all I/O operations must be encrypted. It means file operations, network, and this kind of stuff. So everything must be encrypted. Protected execution, the code must run in protected environments. Sealed storage. Sealed storage is a really interesting concept. It's basically is the process of encrypting secrets for persisting storage to the disk. So if I restart the CPU, the secrets are still there and they are not turned down. We have like remote attestation. Basically, a client's enclave can test remote entity that's trusted and establish authenticated communication channel with that entity. It's possible to know if the code was tampered or not. And of course, like we have like this trusted third party. But like how it works with Intel or like other CPU vendors. So what they did, now we have like a new party here, the manufacturer. So you should trust the manufacturer. So we should trust Intel. It's scary, yeah. I mean, you need to trust someone. Sadly, it's Intel, but like, the whole idea here is now the manufacturer builds this, has this trusted hardware here, and it's able to hide the details of it from this infrastructure owner. So what happens is, it's almost like this previous slides. I, the data owner, want to send the data to the cloud, and the data is loaded, the code runs there, and I am able to receive back the data, and I am able to ask a few questions about this data as this data was modified, this data, the code I run there is the same code I sent to you previously, so I'm able to make those questions using like the manufacturer. So in the end, SGX as reverse sandbox. Like normally, if you know how a sandbox works, it protects you from outside world. SGX Inclave protects you from the world, like inside the world. It protects you from yourself. Let's keep it this way. It protects you from like the CPU. It protects you from the hypervisor. It protects you from the kernel. So imagine, I don't know, if you are a fintech or like even a bank, sometimes you have like some stuff in the cloud, but some machines in house, and you do that because you want to make sure no one is changing the code inside those machines, changing the database. And with like SGX, everything can live in the cloud. But again, you must trust someone, and normally you must trust Intel. So like I said, it protects you from the BIOS, hypervisors, ring 0 to 3, like kernel and things like that, applications, Intel SSM and ME, and it also protects you from remote attacks because we have this concept of remote attestation. But how it works in practice? So basically we have like, when you create Enclave, you have basically two applications. So we have like the main application, and we have Enclave. You can think about two different processes. So when you create Enclave, you need to have an entry point. And this entry point, I call it here like the seal data function. And the way to call the seal data function, you use the equal, we can call like command, with the equal command, and from the app. So you send it to the Enclave, and the Enclave itself can call back other like function called equal back to the like application. So the trick thing here is equals are not safe. So for example, every time you want to do like a file operation, you cannot do file operation inside enclaves. In fact, now you do, but you cannot do like you cannot print stuff inside enclaves. You cannot use system calls inside enclaves. So instead of doing a system call here inside enclaves, you could do the ucall, I don't know, printf. My interested code would be the printf, and you could send back the code to the app, and the app would print my data. So this is how enclaves works a little bit. So enclaves are a little bit tricky because the thread model is different. I mean, if you work with security, you should never use a thread in the first place. System calls are not allowed. So it's a little bit tricky, especially like think with Idris, there is a bunch of like function in the runtime system. We need to care about like system calls, file operations are not allowed, network calls are not allowed, and all this kind of stuff. And basically, it's impossible to make a system 100% secure. And those are all the SGX bugs. So in fact, like it's impossible to make a secret hardware extension. Like I'm not saying you should not use it, like a bunch of companies are using, but when you think about security, security is not about silver bullets. Security is about adding layers and layers of protections, and SGX could be one layer of protection, and it's going to help out like to solve few problems, but again, everything should be used with a grain of salt. So, but why Idris? Like I think like a bunch of you knows why Idris is interesting. Basically, it's a general purpose language. It's not just used to program programs. It's also about running real life production applications. It has first class dependent types. So in the end, functions can compute types can contain values. The syntax is similar to Haskell. So if you're a Haskell programmer, you are not going to need to learn a bunch of stuff to become like a proficient in Idris. It's compiled. In fact, it generates code. So it is why I used Idris on Enclaves here, because I was able to generate. So Idris generates the C code, and in fact, I run in the generated C code inside the Enclave. So we have like also strict evaluation order. It's really important to talk about that, especially we have like a bunch of Haskellers here. And we also have like a great FFI API. I use that a lot as well, like because I need to export, import few information from the enclaves, and it's written in C. So I use the FFI to do a bunch of like calls to C and also to call Idris. But like I said before, we had a few challenges. So we start to try to integrate Idris inside the enclaves. I had a few challenges. And the first one was Graceful Failure. So when Idris, so this is basically code inside Idris. It's like inside the Idris runtime system. So when something goes bad, it's crash, and it's basically terminates the calling process. And also when a stack overflow happens, it also exits. And this kind of stuff cannot happen inside the enclave. You cannot exit enclave. You need gracefully fail inside the enclave. I didn't figure out how to fix that. I just commented on the code. But like, I think the trick part here is because this piece of code here is really deep inside the Idris compiler runtime system. I need propagate like deception up until the virtual machine and return back to the enclave. So maybe using callbacks, I still figure out what's the best solution here. Like I said before, so those are like a few, again, Idris, runtime system APIs. We cannot use that because IO is secure by default. Luckily, SGX has few APIs to handle like the standard file system calls. So I need to change a little bit. The tricky parts because Idris use system calls to get, for example, the file size and this kind of stuff, and we cannot use that. So I need to implement a bunch of stuff using those standard functions here. But again, it was not that bad. However, it makes things a little bit slower. And also, like I said before, system calls are not allowed, so we cannot use any of like natural calls there inside like the enclave. And enclaves have the ARM multi-thread model, like I said before. So, but as I said before as well, like if you are using threads inside the enclave, you are like, I don't know, a psychopath or something like that. Because enclaves must be a piece of trusted code. If you have threads and trusted code in the same sentence, is a little bit dangerous to do that. Like you should like never use like threads inside Enclave. Basically, Idris has a piece of like of threads inside the code, but luckily we can disable in compile time. So it was not a big deal. I just disabled it all, and life was much happier without that. But like when we when start to think about, oh, how can I start that? How can I put a Idris code inside a Enclave? So the first thing I did was, okay, let me try to print something on the screen. It's a good start, right? Let's print. So I think the first thing when we work in an Enclave, we need to have like the Enclave definition lang. Basically, it's a file, it's an EDL file, and basically it says you need to put like mainly two things, the trusted and the untrusted function calls. So the trusted is that code being implemented inside the Enclave, the call Enclave, and the untrusted code, the Enclave can call the application back. And the second step was creating the Idris code. Like I said before, I used the FFI_C keyword to access the function and call it inside the app. So this is basically one simple hello world using. So this Idris code is running inside the Enclave, the SGX Enclave. And basically, like, again, I am getting the call prints. The call prints a C code they created just to print some stuff. It's like basically a printf on C. And I call in that. So how it's working. So inside the app, and the app could be anything. Could be, I don't know, a Haskell, could be a Go, could be, I don't know, ATS, could be anything. And inside the app, I call Inclave. And inside the Idris, the Idris call Inclave was called. I instantiate the Idris virtual machine and sent back the call print back to the app. So this is basically what this is doing here. So, however, there's like big problems here. The first thing is everything lives in the global scope and it sucks. And it's not easy to send secure data back to the app. So I was thinking about, okay, what kind of hack I need to do to make it work great. And look inside Idris code, I was able to figure out there is one thing called FFI_exports. Basically, it's like, it's not undocumented. It's not documented. However, there are a few unit tests. I was talking with like Idris creator and he told me, you should not use that because it's, again, no one used that, but life's not fair, right? So I decided to give a try and end up being the best solution. So the same thing now, but now my trusted code returns some data and I could also like add a bunch of arguments here in the function. I also stick with the call print here because it's cool to have like a way to see things running on the screen. And basically, I created also Rascal code to auto-generate a bunch of stuff for me. So the first block is auto-generated. The 7 to 11 is not auto-generated, and the 13 to 16 is auto-generated. And my random number here is not random at all. But like the cool thing here is from the lines like 13 to 16, Idris generates for me that like a header file, and I am able to embed it inside the Enclave. But basically, what it means runs inside the Enclave. So that piece of code, like I think it's like 400 lines of code, but it's basically like that. Like the Idris C generator transform that thing in this plus a bunch of other stuff. So the first thing, and also this kind of stuff here is auto-generated. So I generated this generates random number here. So the first piece here from the line 1 to 9 is the Idris generated for me. So that code here is basic. So the generate random number in the line 10, 11 is one to the line is the line 1 to the line 9. So that things it generates for me. The other things 11 to the line 16 I generated, and basically I instantiate the VM, calling back the function and closing the VM. So one of the problems I still have is because for each Enclave I need to instantiate the VM. So it can have like additional bottleneck, especially when you're running Idris. But normally like the Idris bootstrap so quickly, like I didn't see any problem in the solution. So how it works? Same thing. The app calls the generate random number. In the enclave, the generate random number function calls Idris VM, like you saw in the code. The Idris VM calls back the call printing and shows something on the screen. And additionally, now we are able to return some data back to the enclave, like here, like the return generated random number. So now it's much better, and we can extend this for any kind of like inputs and outputs. And the good thing now is because now you can do anything it is possible to do with Idris. You can have like theorem prover. You can like create like, I don't know, cryptography primitives, type safe cryptography primitives, and everything like that. So this was one of the biggest advantage of using Idris. It is because we have like now the whole Idris power inside the enclave, and the developers are not going to mess up too much anymore. So thank you. I'm going to put the code's not there yet because it's a mess. I'm going to put the GitHub, like the code inside that repo here, their organization. And thank you very much.